This is the beginning of Chapter 2. Chapter 2 is about variation and graphs. So how do things relate to each other and then their graphs. For Lesson 2.1, it's about direct variation. So things are going to relate to each other directly. As one increases, the other will increase, or as something decreases, the other will decrease as well. And that's a good definition of direct variation. Both quantities increase or decrease together. As you can see, I typed that definition in the box. And then the next thing we're going to talk about is the constant of variation. That is a non-zero constant, or a non-zero number. And I'm going to write the formula for you so you can see how that is and what it is. So I wrote that definition in there. And you can see the formula y equals k times x to the nth, where k is the constant of variation. So that's what k would be equal to. So in the box you can see definition of direct variation function. A direct variation function is a function that can be described by a formula of the form y equals kx to the nth. With k cannot equal 0 and n has to be greater than 0. All this is it's a function where two things relate together the same. So as one increases, the other increases. So as y increases, x increases, or if y gets smaller, x gets smaller, or as x increases, y increases, and so on and so forth. So when y varies directly as x to the nth, we also say that y is directly proportional to x to the nth. For example, the formula a equals pi r squared can be read, the area of a circle, so that's a is the area, is directly proportional to the square of its radius, which is r squared. So in other words, as r, the radius, gets bigger, the area is going to get bigger. They relate directly to each other. In this case, pi is that k value. It's that constant of variation. It's that number that cannot be a 0. Let's work through this first example so you can see this. Okay, example 1a. The volume V of a regular icosahedrons is directly proportional of the cube of the length L of an edge. That's a lot of mumbo jumbo, it sounds like. But let's work through it. So identify the dependent and independent variables and write an equation relating to them. So we know that volume equals, it has to do with relating to the length of the cube. So we're going to relate volume to length. So volume is directly proportional to length. So in this case, volume is directly proportional to length. As length gets bigger, the volume is going to get bigger. So length is the independent. It's the controlling one. And volume is the dependent. It's the result of that length. So we're going to figure out, we have the length, and we're going to get the volume from the length. So length is independent and volume is dependent. In this case, we can say volume equals KL cubed. And we know it's cubed because it's volume. So n would equal 3. Because if we remember back to our direct variation, y equals kx to the nth. So volume equals KL cubed. So a regular icosahedrons with an edge length of 4 centimeters has a volume of about 140 centimeters cubed. Determine the constant of variation, k. So we have volume equals k times length cubed. So we know their volume is 140 centimeters. They tell us that. So 140. We are trying to find k, that's that constant of variation, to see how they're relating to each other. And we know the length is 4 centimeters. 4, and then we have to cube it. So we say 140, we're going to simplify this, equals k times 4 cubed is 64. We're going to divide both sides by 64, and k equals 140 divided by 64, which is 2.1875. That's the constant of variation. That's how they're relating to each other, the volume and the length. Part C, rewrite the variation equation using your result from Part B. All we have to do is use that y equals k times x to the nth, that direct variation function, and we're going to rewrite it with our new k that we have. So we can say y equals 2.1875 x to the nth, but we're going to replace the y and the x with the volume and the length. So we can say volume equals 2.1875 length cubed. That is our equation. And then in part D, approximate to the nearest cubic centimeter the volume of an icosahedron with an edge length of 5 centimeters. So we can say volume equals 2.1875 length cubed. That's our variation equation. We're trying to find the volume, and we have a length of 5 centimeters. 5 cubed is 125 because we have to do our exponents first. So volume equals 2.1875 times 125 is 273.44 cubic centimeters. Okay, we're going to keep working through some example problems. In 1b, the surface area S of a cube is directly proportional to the square of the length E of an edge. So identify the dependent and independent variables and write an equation relating them. So E is the length of an edge. That's the independent. Because in order to get the surface area, we would need to know that length E. So that surface area S, which they talk about, is the dependent. It is depending on that length E in order to solve that surface area. So we could write this as S equals K times E squared, because an area equation uses squared instead of cubed, so that's why we know we have that n equals 2 or that squared term. So that's our formula we're going to use, or our function. Part B, a cube with an edge length of 5 centimeters has a surface area of 150 cubic centimeters, or not cubic, squared centimeters. Determine the constant of variation. That is K. We're going to solve for K. So we can say S equals K E squared. We know we have a surface area of 150, so 150 equals K times the edge length is 5 squared. We're going to solve for K, so we have 150 equals K times 25, because 5 squared is 25. Divide both sides by 25. And you should get K equal to 150 divided by 25 is 6. So our constant of variation is 6. Now we're just going to rewrite that variation equation we used at the beginning here and plugging in our value for K. So we can say from that S equals K E squared, we can rewrite it and say S equals 6E squared. Now, what is the surface area of a cube with an edge length of 8 centimeters? So we have S equals 6E squared. We're trying to find that surface area S, but this time we have the edge length of 8, and we have to square it. So we're going to plug 8 in for E and square it. So S equals 6 times 8 squared is 64, because you have to do the exponents first. 64 times 6 is 384 squared centimeters. That is the surface area of a cube with an edge length of 8 centimeters.